Good afternoon. This is an important question. Draw the portion of the iron carbon diagram used for steel. This is the portion. Write the names of the lines and the phases. Explain how some of the useful lines are for heat treatment. So we have to write about this. So then the portion of the iron carbon diagram. This is the portion of the iron carbon diagram which is very relevant for the heat treatment. So in this portion what you require is to give this line A3, ACM and then this A1. This part is very important. So the first part, write the names of the lines and the phases. Now you mark the phases which you have found, that is austenite, ferrite, austenite plus ferrite, austenite plus cementite. So these are the phases. Explain how some of the lines are useful for the heat treatment. Now how these lines are useful, that is very important thing. So in that case we have to know some of the important terms. Is that austenizing temperature. The first important thing is austenizing temperature, where 100% austenite is found. Then austenitic reaction, when the temperature is 723 degree, when we cool below 720, first austenizing temperature. It may be anything, any temperature above 723. It would be. You will see it from the diagram. That is the important thing. Then when cooling, when we cool below 723 degree centigrade, there the austenitic reaction occurs. So these are the two important things. So sample is taken at the room temperature, then it is heated to the austenizing temperature. And this temperature, which is decided by A3 and ACM, is important. Then depending upon the sample, we have to find the duration time, heat duration time, which depend on the dimensions of the sample. So after that heating, we have to cool the body. The cooling rate can be different. Here, the cooling rate is decreasing. Increasing. This is the slowest cooling. The top one is the slowest cooling rate. In that also you can have two types of cooling rate, slow. Then here we get fine and coarse perlite. Afterwards we get, if the cooling rate is far faster than critical cooling rate. Critical cooling rate is decided by this nose of the TTT curve. If we draw the TTT curve, this is the nose of the TTT curve. This is the line. This is the critical cooling rate, which is tangential to the nose, and any cooling rate faster than this, they form the critical cooling rate. So these are the above critical cooling. So any cooling rate faster than this is the critical cooling rate, this will give martensite, and any cooling rate in between these lead to the formation of bainite or sorbite, like this type of microstructures. So we have to know all these things. So the important thing is A3 and ACM. These lines are very important, and A3. So if you come here, suppose we have got any steel, this is a 0.8%, and for this is a 0.8% carbon steel. Okay? For this you have got 723 degree centigrade. Matlab 0.8% carbon, if you heat at 723, it will austenize. But what about this, which is at a composition 0.4%, let it will be 0.4%, which is less than this. Then you have to see this, draw a line parallel temperature line, and here it cut the A3 here, and this temperature, which may be about 800 degrees centigrade. So this is decided by this A3 line. And now you have to heat at any temperature for 0.4, you have to heat about, that is, we get it from nearly 800, then 850. Yeah, 815, you can say 815 or 820 degrees centigrade. You have to heat it at 815 or 820 degrees centigrade. So similarly, if the temperature, it is 1.7% carbon, if you see this, it is 1.7%, yeah, 1.5% carbon. So you will cut it here, and this line may be, any temperature may be around 1000 degrees centigrade, because it is 910 is here, to 1000 degrees centigrade. So we will find that for 1.5% carbon, we have it around 1000 degrees centigrade. We can heat a bit temperature lower than this. That is 1.5%, you have 1000, and we can heat up temperature above this, that is 120. But what happened this, with this higher carbon, the problem is that when we cool it, when we cool it. So if you see the microstructure, this is a steel and these are the grain boundaries. So what happens when we cool it at below 723 degrees centigrade, means here in this region, if we are in this region up to here, what will happen? The cementite will develop at the grain boundary. This grain boundary is cementite. These are called pro-eutectoid cementite. Pro-eutectoid cementite. These they form the network and they may be brittle. Depending upon the temperature and the duration, this network will be very long. If they are continuous network, then they will lead to crack propagation. So in that case, either we try to heat it just above this A1 line, or if we are forced to heat it at up to ACM, then we have to heat it for low carbon steels and for a very short duration, so that this network is not formed. So this is the importance of this line. After now, comes the next stage is the cooling stage. This here, this is the cooling stage. If you see this, the rate of cooling is here. So after this is the austenizing temperature, where it may be anything what you have got from the A3 or ACM line. So depending upon that, you can cool it. If we cool it at a slower rate, we will get perlite, and if we cool it at a faster rate, then we will get martensite. Martensite is got above when we cool it at a faster than critical cooling rate. Here the reaction occurs is that austenite is converted into ferrite, cementite plus ferrite. These are the alternate plates are formed. Like this is the microstructures. If we have like this, alternate plates of ferrite and cementite. These are alternate plates of ferrite and cementite. Ferrite, cementite. And whole thing is called perlite. So in this way, this is the importance of all the cool lines shown in this for the heat treatment of the steel. So with this, we end this lecture. Thank you for hearing. Okay, bye.